Calcine is a patented, innovative, proven solution for problems caused by sodic and saline sodic soils. It's formulated from natural ingredients like organic acids, amino acids, L-glutamate, and yucca extract. It's easy to mix, can be applied by a variety of methods, and because it can be used in conjunction with other products, it adds little to equipment or labor cost for its application. By reducing sodium levels, calcine improves the soil structure and increases and balances overall soil porosity. Improved water movement makes leaching of salts and chlorides more effective. When dealing with sodium and salinity problems, it all begins with water and calcine. To understand calcine's effect on the root zone, we need to learn a little bit about soil colloids and soil ions. We'll see how calcine makes the calcium already present in the soil more available. Free calcium then displaces sodium from the root zone. We'll also see how available calcium improves soil structure and porosity by helping to convert dispersed soils into flocculated soils. Finally, we'll see how all this adds up to removing more salts and chlorides from the soil. Colloids are extremely tiny, with a diameter no greater than 1/10,000th of a millimeter. We can get a perspective on just how small this is if we compare them to other soil particles. This is the surface of a single grain of sand with a diameter of 1 millimeter. Silt particles have a diameter of 5/100ths of a millimeter. Clay is at 2/1000ths of a millimeter. And finally, colloids are no larger than 1/10,000th of a millimeter. This relative size becomes even more clear if we pull back and compare them to the full size of a grain of sand. Colloids are the most active component of the soil and determine both its physical and chemical characteristics. They can be either mineral or organic in nature. Their surfaces are negatively charged and attract positive mineral ions. Nutrients and other elements exist in the soil in the form of ions. An ion is an atom or molecule that has either lost or gained electrons. This gives them either a positive or negative charge, which can be seen in their notation. Cations are positive, and anions are negative. The terms monovalent and multivalent describe whether an ion has either single or multiple charges. For example, sodium is monovalent with a charge of +1. By comparison, calcium is a multivalent cation. This difference will become important when we see its effect on soil structure. Calcium is abundant in soil in the form of calcium carbonate. However, in this form, it's insoluble and largely unavailable. The addition of calcine solubilizes calcium carbonate, and this process releases carbon dioxide, water, and most importantly, free available calcium ions. Soils have a limited capacity to exchange cations. Estimated sodium percentage, or ESP, measures the amount of this capacity occupied by sodium. An ESP greater than 15% is considered to be a sodic or problem soil. This image depicts a soil with excessive sodium levels, which must be lowered to increase its productivity. Free calcium ions produced by calcine's effect on calcium carbonate will displace sodium ions from the soil colloids. This soil is now much more productive. Soil's very fine particles can be found either grouped together into larger granular or crumb structures called flocculated, or they can exist independently isolated or dispersed. Dispersed soils have several management problems. They're resistant to water infiltration, which can lead to runoff and increased evaporation. They also have a tendency to form a surface crust. Flocculated soils, on the other hand, due to the freer movement of air and water through the profile, provide a much healthier growing environment. Characteristics of a dispersed soil are less porosity, tendency toward compaction, poor water movement, reduced root depth and mass, subsequent reduced nutrient uptake by the plant, surface crusting and runoff, and less bioactivity. Having only one positive charge, the sodium ion does not flocculate soil. In fact, when present in high concentrations, it acts to disperse soil. In addition, its large size and hydration or water shell further break down soil structure through swelling. The characteristics of a flocculated soil are more porosity, less compaction, better water infiltration, greater root depth and overall root mass, subsequent better nutrient uptake by the plant, and more bioactivity. With multiple charges, calcium ions do act to flocculate soil. This image depicts calcium's role in soil flocculation. As we've seen before, soil colloids have a negative charge. The free calcium ions produced by calcine's effects, because of their multivalent nature, can bond soil colloids together. This effect can be described as an ion bridge. Textbooks often describe ideal soil structure. While it never seems to exist in nature, it goes something like this: 45% mineral, 25% water, 25% air, and 5% organic. What's important about this structure is that it depicts soil as being 50% solids and 50% pore space, equally divided between macropores filled with air and micropores filled with water. Because of calcine's effect on soil structure and flocculation, it provides greater overall soil porosity and a better balance between macro and micro pore spaces. Field capacity describes the amount of water a soil can hold after free gravitational drainage. Macropores are filled with air at field capacity and increase soil's permeability. Micropores hold water at field capacity and increase the soil's ability to hold plant-available water. Being negatively charged anions, chlorides do not bond with soil colloids. They are found in solution in the water in soil pore spaces. Along with soluble salts, they are easily leached from well-flocculated soils, as can be seen in the following demonstrations. Laboratory research was conducted to measure calcine's performance in two areas: its effect on water retention at field capacity and its effect on salts leached from the soil. Tests were conducted on a control sample and samples representing 1/4 gallon of calcine applied per acre and 1/2 gallon of calcine per acre. The same amount of water was applied to each sample. Free drainage was reduced with each increase in the calcine application rate. Likewise, water retained increased in the same fashion. Salts flush increased as the application of calcine increased. When it comes to solving problems with sodic and saline sodic soils, it all begins with water and calcine.